Let's understand a very important idea in statistics called hypothesis testing. It's a very, very confusing idea. It's a very, very confusing idea. So please bear with me and try to follow me carefully. I'll try to elongate this video slightly. I'll try to go as slowly as possible so that you're following me very clearly. This is a very, very confusing idea. So we have to be very, very cautious when we try to go into the details of this idea. Right? So I'll try to explain this idea with an example so that it makes life simple. The example is as follows. Let's take a first example, right? Our example one is as follows. We'll try to understand it from multiple examples because that way the concept becomes clearer instead of going through the theoretical route, right? So let's assume we are given a coin, right? So given a coin, right? We want to determine. We want to determine if the coin is biased towards if the coin is biased towards heads or not. If it's biased towards heads or not. We are not talking about tails. We are only talking about of the coin being biased towards heads or not, right? So what does it mean? So what does it mean to say that the coin is biased towards heads? So what do I mean when I say the coin is biased towards heads? It means that the probability of getting a head when I throw this coin or when I toss this coin, the probability of getting a head is greater than 0.5. This is what I mean when I say the coin is biased towards heads. When I say the coin is not biased, when I say the coin is not biased towards heads, it means that the probability of heads is equal to 0.5. Right? This is what I mean. So I'm just trying to make my definitions clear here. Right? Now, given this task, so this is the task we are given, and we want to determine this. You're given a single coin, and we want to find this out. And we can answer questions like this using the idea of hypothesis testing. Instead of explaining you the terminology of hypothesis testing, let's try to solve this problem using basic probability. Using basic probability, let's try to solve this question, right? Let's see how it goes. So the first part of this task is I'll design an experiment. I will design an experiment. Let's assume my experiment is this. My experiment is to flip a coin 5 times. And this is my experiment that I'm designing, right? And who designs this? The final problem that we want to solve is this, right? As a stats guy, my job is to design this experiment. My experiment that I'll design is this, that I'll flip a coin 5 times and I count the number of heads, right? This is what I define as my experiment. And let's say the number of heads I count is, let's say, capital X. Right? I'm saying that the number of heads that I get, okay, when I flip my coin 5 times, let's call it a random variable X. So X here is a random variable, right? It's the number of heads that I get when I flip my coin 5 times, right? This is what I'm calling it. Now this X often in statistical literature, in the theory of hypothesis testing, this is called a test statistic. You don't have to worry about the terminology. We'll pick up the terminology later. The concept is important, right? The concept is important. Terminology, you'll pick it up as and when necessary. And you'll pick it up as you try to repeat this concept multiple times, right? So you're counting the number of heads and you're calling it capital X. It's a random variable and we call it the test statistic, right? This is the test we're doing, or this is the experiment we're doing. What is the experiment? That I flip the coin 5 times and I count the number of heads. And the number of heads is nothing but your test statistic. Now let's say this is, you've designed here you're defining or you're designing the experiment, right? Now you perform the experiment. Let's assume I perform the experiment. When I perform the experiment, I'm flipping the coin 5 times. So let's say I flip 5 times. I flipped the coin. That's what I defined my experiment. In the first flip, let's assume I got a value of head. In the second flip also, let's assume I got a value of head. Same heads. All the 5 flips, let's assume I got 5 heads. when I perform the experiment, right? When I perform the experiment, I got 5 heads. Then what is the value of x? X is basically the number of heads. My x equals to 5. Remember, I actually did this experiment and this is what I observed. This is my observation. This is my observation from performing the experiment, right? So my test statistic, my test statistic is x, right? So my test statistic on observation is 5. I'm trying to use this terminology so that you get used to this terminology, right? So when I performed the experiment, I found I got 5 heads, which means my test statistic has a value of 5 when I made the observation by experimentation. I made this observation by experimentation, by performing the experiment. Now the question is this. We did this experiment, we designed the experiment. Now comes a very, very fun part. Now I would ask the question. The question I would ask is, what is the probability of x equals to 5 given that the coin is not biased towards heads? Right? I try to ask this question. This question is very interesting. So here, this is a conditional probability, right? What does this mean? You're making an assumption first. This is an assumption you're making. You're first assuming that the coin is not biased and you're saying, what is the probability of making, this is something that you have already observed, right? You have observed when you perform the experiment once, you observe that x equals to 5, right? So what is the probability of the observation given this assumption, right? So in hypothesis testing, this assumption is called a null hypothesis. It's often written as H0, right? So what is our null hypothesis? What is our H0 or null hypothesis? Don't worry about the terminology. You'll pick up the terminology as I told you. Our null hypothesis here is that the coin is not biased towards heads. This is a null hypothesis. And what is our observation of the test statistic? So it's a little tongue twister, especially for me. So our observation of the test statistic is x equals to 5. So what is the probability of making my observation given the assumption? So this can also be written as probability of observation given my null hypothesis. Because this is what I said is my H0, right? Can I compute this now? Let's try to compute this using simple probability and combinatorics. Very, very simple. Let's try to compute this probability now. Okay. So let's say probability of what we want to compute is probability of getting 5 heads. What is this? This is nothing but 5 heads. 5 heads. This is probability of getting 5 heads in 5 coin tosses. In five tosses. Probability of getting x equals to 5 given our null hypothesis. What is our null hypothesis? Our null hypothesis is that the coin is unbiased. Coin is not biased towards heads. That's a null hypothesis, right? Can we compute this? Now imagine if I have a coin which is not biased towards heads. If I flip it 5 times, right? I flip, right? When I flip it 5 times, in the first flip, there is a 1/2 chance of it getting head. If my coin is not biased towards heads, what does this mean? Let's try to understand this. What does this mean? This means the probability of getting a head is equal to 1/2 or 0.5. That's what this means, right? Right? If my coin is not biased, it means my probability of getting head is half. So you're trying to see what is the probability of getting 5 heads in 5 tosses if probability of getting a head is half, right? So what is the probability of getting a head in the first flip? Half. Or first toss? Half. Second flip or second toss is half. Second one half. Third one half. So the probability of getting 5 heads in 5 tosses, assuming that the coin is not biased, or assuming that the coin has this probability, the probability of head is exactly equal to half, is 1 by 2 power 5. I'm just making this multiplication. The other way to think about it is, when I flip the coin 5 times, for every flip there are 2 possibilities. So across the 5 flips, there are 2 power 5 possibilities. This is simple combinatorics way of understanding it, right? There are 2 power 5 possibilities or 32 possibilities. Of these 32 possibilities, there is only one possibility where you get all 5 heads. So let's look at it. You get head, 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 right? You get head, 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 tail. So if you keep writing all the possibilities, you will get 32 possibilities, right? Because you can think of each of these values can be a head or a tail. So there are a total of 32 possibilities, of which only one possibility is all heads, right? So this is nothing but 1 by 32. 1 by 32 is roughly equal to 0.03, roughly, right? This you can read it as 3%. And remember, this was easy to compute, right? Computing this probability was easy, and that is very important. We compute this probability using simple ideas in combinatorics. A very simple idea in probability and combinatorics. We just use the simple idea, right? So what do I get now? I get the probability of x equals to 5 given my null hypothesis is 3%. Is 3%, right? So let's try to read it in English. So I'll try to write it so that it becomes clearer for you. What it says is that there is a 3% chance or probability of getting 5 heads, of seeing or getting 5 heads in 5 tosses or 5 flips if the coin is not biased, towards heads, right? I'm trying to read this in English and you read it like this. There is a 3% chance of seeing 5 heads in 5 flips if given, you can read it as if or given, that the coin is not biased, right? And hypothesis testing works like this. So we computed this whole idea. So hypothesis testing works like this. It says, so here remember, I've already made this observation. That x equals to 5 by doing the experiment once, right? So what hypothesis testing works like this. It says probability of observing what you have observed, probability of observing by experimentation, right? Given that the assumption is true. Is 3% here? Right? Let's try to understand it this way. I performed the experiment once and I observed a value. What was my observation? That x equals to 5. Right? I performed the experiment and I made the observation. The probability of this observation by performing the experiment, if the assumption is true, if our assumption or hypothesis or null hypothesis is true, what is our assumption? Our assumption was null hypothesis, right? If you see here, we assume that the null hypothesis is true, right? So the probability of observation given assumption is 3%, which seems quite low, right? So if the assumption, because I've already observed this is ground truth. This is something that I've already observed. This is important to understand. I've already made this observation. Nobody can fight with that observation because it's data. It's data that I've already seen. Nobody can fight with this, right? So given that this observation has already been made by experimentation, the probability that this observation is true, if the assumption is also true, is only 3%, which is quite small. This is quite small. Typically what we do here, so this probability value is called as p-value in hypothesis testing. So p-value, simply think, if you want to think about it from an English perspective, right? If you want to think of it, it's basically the probability of making the observation that we already made given the assumption. What is our assumption? Our assumption is nothing but a null hypothesis, right? Now this value is very small. Let's assume our p-value, this is called p-value, right? This p-value is small. Typically, we say it's small if it is less than 5%. Typically, I mean, this is just a rule of thumb. There is no hard and fast rule about the 5%, right? 5% is typically a rule of thumb that people take. So we say that the probability of making the observation that we already made, given our assumption or null hypothesis, if it is less than 5%, then if this is the case, then probably then our hypothesis, our null hypothesis, our assumption may be incorrect. It may be incorrect, right? Because if the assumption was right, see, we are doing this conditional probability here. So here is the leap of hypothesis testing. We are saying the probability of observation given null hypothesis is very small, right? Hence, H0 must be incorrect. Because observation is not incorrect. Remember, observation is not incorrect because we already made this observation. We already saw that x equals to 5. This is ground truth. We have already seen this. This is an assumption we are making. Since this value is very small, we typically take a cutoff of 5%. Then it is probably that the hypothesis or the assumption we made is incorrect. So we will conclude that, right? We will conclude that our assumption or null hypothesis is not true. Or in other words, we reject our null hypothesis. And what is our null hypothesis here? Our null hypothesis, we reject the idea that the coin is not biased towards heads. And what does this mean? This means we accept the idea. Rejecting the idea that the coin is not biased basically means we accept the idea that the coin is biased. This is called alternative hypothesis. For every null hypothesis, there is an alternative hypothesis. In our case, the null hypothesis was that the coin is not biased towards heads. Our alternative hypothesis, which is often written as H1, is the exact opposite of this. It is the coin is biased towards heads. So rejecting H0 is equivalent to accepting H1. Similarly, rejecting H1 is equivalent to accepting H0. I'm trying to introduce you to the terminology of null hypothesis, alternative hypothesis. But the idea is very simple. Remember, the very important idea here is that we've already made the assumption. So we've already made the observation, So the observation is not incorrect. Probably the assumption is incorrect because the probability of it finding in our case was only 3%. This is very, very important. Very, very interesting and important concept that often people get confused with. Right? Now let's say, so here I've made a couple of very interesting ideas. When I designed the experiment, I said I'd flip the coin 5 times. Why do I limit it to only 5 times? What if I do 10 times? Probably my values will change. If I do it 3 times, probably my values will change. My probabilities will change, right? So this experiment that we have designed is dependent on how many flips I have done. This is often called as the sample size, right? So I've taken 5 times, but I could have taken 3 times, 7 times, 10 times, 50 times, right? So the outcomes, for example, let's take an example. Let's say I've said that I flip 3 times. Suppose my experiment. So our initial experiment, let's call it EXPT. Let's assume I have a new experiment, experiment 1. In the experiment 1, let's say, if I said that let's flip the coin 3 times instead of 5 times. This is my new experiment, completely independent experiment from the previous one, right? So my new experiment 1, let's assume, was flip the coin 3 times and count the number of heads. Counting the number of heads again is my test statistic. Right? So now let's assume I flipped 3 times. Flip, flip, flip. All 3 times, let's assume I again got head, head, head. Let's assume this is I performed the experiment. When I perform the experiment, let's assume I got this. So my x equals to 3 is the observation. I got. So what is the probability of observation given my null hypothesis, given my assumption? What is my null hypothesis again here? My null hypothesis here is that the coin is not biased towards heads. Is not biased towards heads. So what is the probability of this observation? What is the probability that you'll see 3 heads in 3 flips of the coin, assuming that the coin is not biased? It's again 1 by 2 power 3, which is 1 by 8, which is 12.5%, right? Which is greater than 5%. Now, there is a 12.5% chance of making this observation if my assumption is true. And this is not too small. This is significant. This is much greater than 5%, right? So in this case, what I'll say here is that I'll accept my null hypothesis. Even though I've seen 3 heads, the probability of seeing 3 heads is 12.5% if my assumption is true. Right? Remember, I've already made this observation, and this observation has a chance of 12.5% of occurring. It has a 12.5% chance of occurring, right? Which is not too small. So I can't reject my hypothesis. Since I can't reject my assumption, I will accept my assumption. So here, by changing my 5 flips to 3 flips, my outcome has completely changed. So you have to be very careful. About your sample sizes. There are 3 things there are a couple of things that are important in hypothesis testing, right? They are very, very important in hypothesis testing. First, your design of the experiment. Right? Here we said, let's flip the coin 3 times or 5 times, right? Whether you choose 3, 5, 10, 50, that is all part of the design of the experiment. You have to be very, very careful and ingenious and creative with designing the experiment. You design the experiment incorrectly, you've gone for a toss. Your whole hypothesis testing is invalid. Second, defining or saying what is your null hypothesis. Designing a null hypothesis is also very important, because your null hypothesis should be so chosen that the probability of computing your observation given null hypothesis is easy to do. Right? Look at this. By just making the assumption, what is my null hypothesis here? My null hypothesis is that the coin is not biased. Under this assumption, computing this probabilities is easy. Right? If my null hypothesis was the opposite of this, I can't even compute this probability. Right? So we have to always design our null hypothesis, or we have to take the null hypothesis, which makes our probability computation easy and feasible. Right? So these 2 things are very, very important. Remember, there is one mistake that a lot of people do. When I say that my p-value is, let's say, 3%, when it is less than 5%, we typically reject our null hypothesis. Right? P-value, this is very important, is the probability of making the observation that we have already made if we make the null hypothesis assumption. If we assume null hypothesis is true. This is what it is. This is the right meaning. Some people think that it's a probability of that the null hypothesis is true. This is a complete blunder. It is not equal to the probability of null hypothesis is true. We can't say anything about this. It is just about the probability of making the observation that you made given the null hypothesis is true. You can't say anything about what is the probability that your null hypothesis is true. This is incorrect. A lot of people people who are not trained properly in statistics make these mistakes. I have seen lots of papers where p-value has been misused. Unfortunately, in medical research, p-value is heavily misused because unfortunately people are not trained properly in how to interpret it. So the simple way for you to think of p-value always is, it is a probability of observation given an assumption. And this assumption is called a null hypothesis. And this observation is what you already observed. Of course, you have to design your experiment very carefully. You have to design your test statistic very carefully. There is a third part here I forgot. The design of your test statistic. Design your test statistic, which is X. And you have to define your null hypothesis such that these probabilities are easy and feasible to compute. And of course, I've seen lot of people, I have made the mistake myself a lot of times in hypothesis testing. So this is a place where a lot of people get confused and make mistakes. It's important to understand it very, very carefully. I hope the basic terminology is clear of what a p-value is, what is hypothesis testing, what is null hypothesis, what is alternative hypothesis, and what is p-value.